I'll start now with the main topic where I'll talk about energy. Those who are in the field of energy, you can see very clearly we start from certain amount of energy and we end up with some certain amount of delivered energy. And all energy services that you have a story behind. We need to get that whole story to see where we are using how much. You can see the details, how in different places energy is lost. Whether it is in a factory, whether it's in a building, we use energy. That energy has a whole story, and we need to understand a little bit about this whole story. You can see, for instance, the industry, you require lighting, you require process equipment, you require motive power, and you require heating and cooling utility. All that adds up to see how much energy that you require for a typical industry. This will vary from one industry to another, depending on the type of industrial activities. Some will have more lighting. For example, if you're going to electronic industry, they will have more lighting, whereas some others will have more process equipment which will require energy, like we heard pulp and paper industry will require more process energy. Some will require more motive power because they're big motors, like in the cement industry. And finally, we'll have heating and cooling utilities. There are industries where mostly air conditioning is required, electronic industry, manufacturing of micro, semiconductor, etc., where you require a lot of heating and cooling utilities in different. And data centers, for example, are one of the areas where you require a lot of heating and cooling. So you can see the demand is building up. The question is, how do you reduce this demand? The same way you can see what happens in commercial buildings, typical commercial building. You have lighting, like in this place, heating, ventilation, air conditioning. We have electrical appliances, more and more electrical appliances we use, whether it's computer, whether it's printers, whether it's fax machine, photocopy machine, etc. And you have other loads like lifts, pumps, all that is included there. You can see the demand is building up with all these different usage. Now we need to understand a little bit, and I'll take up one specific case. I'll talk about what happens exactly, the whole chain of conversion that takes place. Starting with fossil fuel, you can see whether it's coal, oil, gas undergoes conversion process, whether it's in a refinery and power plant. Automotive gave you the figure, 35% of the coal is actually converted into electricity. So already we are eliminating 65% which is gone here. We are left only with 35% of electricity. That electricity needs to be transported from far away distances because the power plant is very often located at the coal head. It has to be transmitted over long distance. This is where you get the final energy coming into the building and industry. Again, there are losses. Every time there is conversion, every time there is transportation, there are losses. And then comes the appliances. We use motors, lamps, process equipment, etc., compressors to get the energy service. And this is what we need for providing services or producing manufacturing. So this is the energy service that we require, and you can see it goes through the whole chain. If you go backwards, you can see each step there are losses. And unless we become aware of it, unless we have a full understanding of how the whole chain takes place in whatever process that we use these services, we will miss the opportunity to improve the whole chain. Where do we need to start from? So we need to have an integrated approach. An approach which gives us a full picture as to, if I act in a particular area, where are the impacts? Now this comes to my favorite slide, which I like to use again and again. Simple one, that's why I started only with lighting. And many engineers come out of engineering schools, you ask them what is the efficiency, they're not able to say this. You can see here, I would require, let's say for a specific task, I require 1500 lumens of lighting. If I use an incandescent lamp, I would require 100 watts lamp. Only about 5% to 10% is converted as light. 90 to 95% is lost as heat. So what I'm particularly interested in is what is the service I get. I don't see what is happening behind it. So my service is equivalent to only 5 watts, whereas I'm consuming 100 watts. When I'm consuming 100 watts in the transmission distribution line, I lose another 10 watts, assuming the system is efficient. In many of the developing countries here, it's not 10%, it can be 15, 20, 25, even we have cases of 30% losses in the transmission distribution. Then we go to the power plant. You can see here, every unit of energy that we produce, we lose 2 units of heat given out to the air, water, whatever is the medium by which you can dissipate that heat. So to get 5 watts of useful energy, we are using 335 watts of energy in coal, oil or gas, whatever you use in a power plant. Would you accept that in reality? I again like to give this simple example. You go to buy a glass of Coke and the server comes with only about 3% liquid and 97% bubble. Would you be happy about it? But we all seem to accept, as you can see, there are millions and millions of incandescent bulbs still being used all over the world. This was something which was discovered more than 100 years back. The technology is still going on because, again, due to wrong policies, because we don't see the whole picture. I took up the case of lighting because it's spectacular. You can see very clearly how the end-use service that you get is only a very small fraction, less than 5% of the energy that is used as fossil fuel, which is taken from the nature. Now, we could think about changing our power plants. Governments are thinking about putting new power plants because there is more need for lighting in many countries because many people don't have access to electricity. We could think about improving our transmission distribution losses. We could also think about how to change this land to make useful land, a more efficient land. We have different options, but the question is where do you need to start so that you get the best results. Okay. I'm taking this one specific example because everything else can be following in the same pattern. So, in the base case, we have 100% energy which is used with incandescent lamp, and we've seen less than 5% of energy is actually converted into useful energy service, which is required by us. Obviously, we don't want to cut down our services. When we need that lighting, it should be there. We're not talking about sitting in the dark and saving energy. Now we see, if you change this lamp, just one small lamp, we change it to a compact fluorescent lamp, we still use that 5 watts of useful energy, but our losses come down from 95 watts to 15 watts, and our consumption from 100 becomes 20. And you can see the cascaded effect. You only require 67 watts. We have achieved what we call a factor 5 improvement. 5 times less exploitation of resources for the same amount of energy service. We have not compromised on energy service. We need to understand this very clearly. How can we achieve? This is where the innovation comes in. A single bulb can lead to achievement of that factor 5. And around the world today, there are many scientists and engineers looking at how to have these technologies by which you can reduce your dependence on natural resources, not 1 or 2 times, but 5 times, the factor 5. We can do better. Instead of using a compact fluorescent lamp, you see we have not changed the power plant. We have not changed we have not done any improvement in the transmission distribution. But the message that we can get is now we can see the same power plant can light up 5 times so that we can meet the unmet demand in many of the developing countries. We can provide more services without really spending more money on power plants, on transmission distribution network. Let's take it further now. As technology evolves, now we are talking about another technology which is light emitting diode. It's not perfect. It's not that efficient. A compact fluorescent lamp may be 50% efficient. A light emitting diode, when you can see what happens. Now we bring down the losses even further. As a result, we have another factor 2 improvements. So we achieve more than what we call factor 10. But just by changing one lamp from the incandescent lamp to LED, we don't have to go through any more the compact fluorescent lamp because the new technology which is already there for us, we can leapfrog and achieve that factor 10 efficiency, by which we reduce our coal demand from 335 to less than 30 now.